The next thing we're going to look at is the unit step function. The unit step function u of t minus a is defined as 0 when t is greater than or equal to 0 but less than a, and 1 when t is greater than or equal to a. It's also sometimes referred to as the Heaviside function, after English mathematician Oliver Heaviside. So if we look at the graph of this thing, it's a piecewise defined function at heart, and it has a jump discontinuity at a. The function has a value of 0. We can see in between 0 and a, and then once t equals to a, the value of the function is then a constant function of 1 throughout. If we look at example, let's suppose we start with the function f of t, which is equal to t minus 3 for t greater than or equal to 0. We know what this graph would look like. It's just a basic line, has a y-intercept of negative 3 and a slope of 2. If we wanted to look at the graph of f of t, let's say times the unit step function t minus 1, then essentially what this would be equal to, right? We know that f of t is what? It's t minus 3, but then the units, the Heaviside function, the step function is going to be 0 for 0 less than or equal to t less than 1, which means this whole thing is going to be equal to 0 between 0 and 1. That's what we see right here. But then once t is greater than or equal to 1, the unit step function is going to be 1. So we get the graph of t minus 3 for t greater than or equal to 1, which would be this part here. One of the ways that this is described in our textbook, which I think is a fantastic way of describing it, is when you apply the unit step function u of t minus a to a function f of t. It's kind of like the idea that the function is off between 0 and a, right? So the portion that we think of as f of t doesn't really kind of appear because everything's going to be equal to 0 there because of the way that the unit step function works. But then the graph kind of gets switched on. It looks like the graph of f of t, but for values of t bigger than a. And that's kind of what the book describes as the function is kind of being on in that case. You can think of a lot of physical phenomena where you kind of have almost like a switching, if you will, like a switch that kind of gets flipped. For example, if you're looking at the amount of electricity in a light bulb, when a switch is off, right, there's no electricity flowing into that filament, but then instantaneously, the instant you flip that switch, it now becomes on, and you have some kind of current that would be flowing to it. The same thing would kind of apply to if you have a situation where something is in equilibrium, where the sum of the forces would be equal to 0, and then if you apply a force to it that puts the thing no longer in equilibrium, then that force is being applied to it for that time on. So a lot of really interesting and really important applications. They're going to require the unit of the application of the unit step function. It also gives us a way to write our piecewise defined functions using the unit step function as well. For example, let's suppose we have the function f of t, which is piecewise defined. Let's suppose that it's equal to g of t for t between 0 and a, and it's h of t for when t is greater than or equal to a. So one of the ways we can write this is we start with the function g of t. So when t is 0, we start with g of t. And this is supposed to be valid up until we get to t equals to a. And at t equals to a, what we would like to do is switch, quote-unquote, g of t to be off. And we can do that by multiplying g of t by t minus a and subtracting it from our original g of t. When t is less than a, then we know that this unit step function would be 0, so this term disappears, and we do get g of t between 0 and a. Now what happens when t is greater than a? Well, then this part is 1, and we get g of t minus g of t, which is going to be equal to 0. And so when t is greater than a, the function g will not be used in our expression for f. But at that same time, once t hits a, we need to turn the function h of t on. And so we can simply go ahead and add, oops, my apologies. We can simply add then h of t times u of t minus a. Okay. So the unit step function is going to give us a really convenient way, oftentimes, to represent piecewise defined functions using a single formula like this. Also, for example, let's suppose we had f of t, get some more practice with this. Suppose that f of t is equal to 0 for 0 less than or equal to t less than a. Suppose that it's equal to g of t for a less than or equal to t less than or equal to b. And then let's suppose it's going to be 0 then thereafter for t greater than b. And technically this should be a strict inequality. So we can write f of t by using the unit step function. So when we start off, it's going to be the function 0. So we start with 0, and this is valid until t equals to a. Don't really need to do much with that. 0 will always be 0. But now once we get to a, we want for g of t to get switched on. So that means that we would need to multiply this by t minus a. So when t is equal to a, this thing will then be equal to 1, and that gives us the g of t. But then g of t itself only lasts between t and b. So we need to switch it off once we get to b, and that can be accomplished by using the unit step function of t minus b. Before we hit b, which is presumably greater than a, because we have this interval notation, this part will be 0, and so we still will get g of t. But then once t is greater than b, this is going to be bigger than a, so this would be 1, this would also be 1, and therefore this factor would be 0, and we do get the 0 for t beyond b. So using the unit step function, we can write f of t as g of t times u of t minus a minus u of t minus b. And I find this example to be extremely helpful when you have a piecewise defined function where one of the pieces starts at a real value and also ends at a real value. The way that we can accomplish this is you just take that function, you simply multiply it by the difference of these two step functions. It's the unit step function of when you want it to turn on, that's t minus a, minus the unit step function of when you want it to turn off, that's u of t minus b. One of the things that we're going to get, actually let's do another example. So I'm going to call this example 5. We're not going to do example 4 that's in the text for our notes, but let's suppose we have the function f of t piecewise defined, and let's suppose that f of t is going to be 20t for 0 less than or equal to t less than 5, and suppose it's going to be 0 for t greater than or equal to 5. We want to practice, can we write this unit step function in terms of, let's do this piecewise defined function in terms of the unit step function. So we're starting off, and this thing is equal to 20t, which is itself, but we want it to turn off, and so we want it to be 0 for t greater than or equal to 5. We can accomplish that by subtracting the function itself times the unit step function of t minus 5. So let's kind of go ahead and just check this if you wanted to. 20t minus 20t times u of t minus 5. Again, the way this would work is it's going to be 20t minus 20t times 0. And that's when t is less than 5, but then it's going to be 20t minus 20t times 1 when t is greater than or equal to 5. This part here is simply going to be 20t. This is going to be 20t minus 20t, which is 0. And sure enough, that would give us the expression for f of t. So our piecewise defined function, written in terms of the unit step function, is simply 20t minus 20t times u of t minus 5. And again, here's another example where it kind of helps. If you start at 0 and you want it to end at a particular real value a, or in this case it's 5, it's just your function minus the function times the unit step function of that t minus a. This brings us to our theorem. This is in the text theorem point 7.3.2, which is our second translation theorem. And what this theorem is going to tell us is how to do the Laplace transform of a function times a unit step function. So, as always, we know that by definition, we use the notation f of s to denote the Laplace transform of f of t. Let's suppose that we have an a value that is greater than 0. And suppose we wanted to do the Laplace transform of the following. F of t minus a times the unit step function of t minus a. The claim is that this is going to be equal to e to the negative as times f of s. So this is our second translation theorem describing how we take the Laplace transform of a function times the unit step function. Okay. This one is actually a pretty easy proof. Let me actually prove this one for us. So if we wanted the Laplace transform of f of t minus a times u of t minus a, we know that this would be by definition the integral from 0 to infinity. It's e to the negative st times the function you're trying to Laplace transform. That's going to be f of t minus a times u of t minus a dt. We recall that the integral is additive, so we can rewrite this as the integral from 0 to a of e to the negative st f of t minus a, that's an ugly u, my apologies, u of t minus a dt, and then adding the integral from a to infinity of e to the negative st f of t minus a u of t minus a dt. And the reason why we can do this is that, remember, u of t, this thing is equal to 0 for t less than a. And that's precisely what this bounds are. These bounds go from 0 to a. So on this interval, u of t is equal to 0, and therefore this entire definite integral is going to have the value that's equal to 0. So what we get is simply the integral from a to infinity, e to the negative st, f of t minus a, and now on the interval from a to infinity, on that interval, u of t is simply equal to 1. So we just get 1 times f of t minus a, which is f of t minus a. And then to kind of finish off the result, we want to rewrite this so that it looks like an f of t. Let's go ahead and do a u substitution. Let's let u, maybe I won't use u because we have a step function called u. Let's call it w perhaps. Let's let w be equal to t minus a. Very easily then, dw simply happens to be equal to dt, and we're going to get the following integral. It's going to be the integral from 0 to infinity, e to the negative s times, now be careful here, if w is equal to t minus a, then I can solve that equation for t, add a to both sides, we see that t is equal to w plus a. This is now going to be f of w dw, and I changed these bounds without talking about it, but let's be very careful here. So when we change our bounds here, so in the new variable w, which is going to go to t minus a, the original bound in t was from a. Well, when t equals to a, hopefully y'all can see this, I'm getting a little bit low on here. So to change the bounds, it went from t equals infinity, from t equals to a, because because w is equal to t minus a. This implies that our new lower bound is going to be a minus a, which is equal to 0. And then when t approaches infinity, w will also approach infinity as well. So the new bounds in the variable w are from 0 to infinity. We're almost there. This exponent here I'm going to break apart. It's going to be 0 to infinity. I can distribute the negative s in. And then because with respect to w, the e to the negative sa is a constant. Maybe I'll switch it around. I'll call it this. It's the integral from 0 to infinity of e to the negative sw f of w dw. But this is nothing more than the definition of the Laplace transform of f. Again, we have the dummy variable w, but it's the same as if you replace it with a t or x or y or anything. So this is simply equal to negative e to the negative as times the Laplace transform of f, which is exactly what we had said.